W12.1 single slit diffraction. Okay, we know something about diffraction already. We know that when you try to send waves through a gap, a small gap or a slit, then they diffract, which just means that they spread out. So they diffract more if you make the gap narrower, and they also diffract more if you use a longer wavelength. So just to remind you what the diagrams look like, if you send waves through a wideish gap, they spread out a bit, but through a narrow gap the waves spread out a lot, they become almost circular. Now with plain white light, all you see is a wider spread out beam, but if you use a really bright light you see something else. So with a laser, red laser, you see something like this. So you've got the wide spread out central pattern diffracted, but because the light's so bright you can also see that there are other fringes, much dimmer but further out each side of the central fringe. So the question is, what's going on there? So here's a picture of a single slit and a screen, and we'll send some laser light through, and it's diffracting, spreading out and forming a fairly wide blob on the screen when it arrives. So if you look carefully to one side you might see this paler fringe next to the central one. Now if you look at the slit, although it is very narrow, it's much wider, of course, much larger than the wavelength of the light that we're using. So we've got sort of parts of the beam leaving from the top of the slit and some leaving from the bottom of the slit, and of course every position in between. So to get from the slit to the central part of the screen, all the beams, all the possible beams are travelling the same distance, so they're all in phase. As you move further away on the screen, away from that central point, some of the beams have had to travel a little bit further to get there. So from the top of the slit here in the diagram than the ones from the bottom of the slit. So they can arrive at this point all with all different phases. So because all the phases are random, they add up to nothing, so you get a dark fringe here. If you go a little bit further you can find that some of them start to get back in phase again. Not all of them, so this spot's a lot dimmer than the central one, but we have got a point where we've got phases that add up to something that is significant. A bit further up you get a dark point again, and then another dimmer fringe. So same repeats at the bottom. So here's our pattern of fringes, and it's all explained with phase difference. So just remember, key points: the slit is small but much larger than a wavelength, and the distance to the screen varies between the top of the slit or one side of the slit and the other. So you get phase differences that can be constructive at the bright fringes or destructive at the dark fringes. So if we have a graph showing the intensity against position across the screen, here's the central bright fringe, and then we've got a dimmer one and a dimmer and dimmer and so on. So if you look, the width of this central fringe is much greater than the width of the other fringes, and in fact the width of the central fringe is exactly twice as big as the width of the others. And there's a formula to give us that. So this is an actual photograph of the laser pattern you would get. So got the central bright fringe and dimmer fringes on each side, and it's superimposed with the intensity graph, so you can see how that works. So the formula: the width of the central fringe is given by W equals lambda times 2d over A. Just to remind you what all the bits are. Lambda stands for the wavelength of the light, D is the distance from the slit to the screen, and A is the width of the slit. And if you're wondering why it's A, the A stands for aperture, which is the technical term for the width of the slit, or the size of the gap. You may have heard that used in photography. Okay, now this is not an equation that you need to know. It's not on the formula sheet, but if they want you to use it in an exam, they would give it to you. But it's quite nice to have seen it at least. Okay, now what they do expect you to know is what the pattern, the single slit pattern, looks like, and to be able to describe key features of it. So in this photograph, we've got the single slit pattern from a green laser and also from white light. So key points are: the central fringe is very bright, much brighter than the others, and the brightness varies, being brighter at the centre. So it's very bright in the middle, fades towards the edges. The central fringe is twice as wide as any of the others. Okay, you can see that in the picture. The brightness of each of the fringes decreases as you go further from the middle, from the central one. The outer fringes are all the same size, all the same width, but remember, half as big as the middle one. And they're much dimmer, so you do usually only see them when you've got a really bright light like a laser.